Every ocean on this planet is temporary, and the proof is frozen into the top of Mount Everest. The summit is seafloor. The sea it belonged to no longer exists. The continents that killed it are still moving at the speed your fingernails grow, and they are lining up to do it again. The last people to stand up there did what almost every climber does. They put a gloved hand flat on a band of gray rock. This film is about what that rock is, and about the day far ahead when the continents finish colliding again. Here is the deal for the next hour. We are going to follow one engine. Backwards into the deepest past, to the mountains it has already built and worn away. Then forward, 250 million years, to the day the continents finish colliding again. What has been measured, I will call measured. The moment we cross into anything else, I will tell you. Start with the question the summit forces on you. What is seafloor doing 5 miles up in the sky? The gray band at the top of Everest has a name. Geologists call it the Qomolangma Formation. After the mountain's Tibetan name, it is limestone. A pale, hard, fine-grained stone that forms in one place only, the floor of a sea. This particular limestone was laid down about 450 million years ago in warm, shallow, tropical water at a time when the largest animals on Earth still lived underwater because there was nothing walking on the land. And the stone is not empty. In samples collected 6 meters below the summit, roughly the height of a 2-story house, below the highest point on the planet, there are broken shells of trilobites, the armored woodlice of the ancient seas. There are fragments of sea lilies, animals related to starfish that swayed on stalks like flowers in the current. There are the tiny hinged shells of ostracods, creatures the size of a sand grain, each one a pair of doors that opened and closed around a speck of living animal. The highest rock on Earth is a graveyard of marine animals. How high it stands is not a guess, and the number is newer than you might think. In December of 2020, China and Nepal finished a joint survey, radar on the summit, satellite receivers, years of argument about whether to count the snowcap, and agreed on a figure. 8,848 meters and another 86 centimeters on top. Stack 29 Eiffel Towers, one on top of another, and you are still below that summit. Airliners on a short flight cruise at about that height. The seafloor is standing where the jets fly. It got there because a continent crashed. India was not always attached to Asia. It broke away from the southern supercontinent of Gondwana and went north, alone, across an ocean, an island the size of a subcontinent with its own animals and its own weather. And in the late age of the dinosaurs, it accelerated. The magnetic stripes frozen into the seafloor record the sprint, something between 15 and 20 centimeters a year. That is the fastest sustained run by any continent in the whole magnetic record, about 4 times India's speed today. a continent covering a full meter in the span of 5 years. Around 50 million years ago, it arrived. India hit Asia. A collision between continents is not an impact. There is no morning of the crash, no sound, no shock. It is a slow, unstoppable squeeze, and it has never ended. It is still running now, and you can watch it on the instruments. Satellites measure India, driving into Asia at 4 to 5 centimeters a year, about the pace your fingernails grow. Stand anywhere in the Punjab, and you are standing on the front bumper of a moving continent. Over one human lifetime, roughly 4 meters of India disappear into Asia. Crust that has nowhere to go sideways goes up and goes down. Under Tibet, seismic surveys find the crust is about 70 kilometers thick, double the normal thickness of a continent. 2 continents worth of rock stacked like 2 mattresses, one shoved beneath the other, and the pile is still thickening. That is why the survey teams keep coming back to Everest with new instruments. You do not keep remeasuring a thing that stays still. So, hold the 2 facts side by side. The rock at the summit says a sea floor can be lifted higher than the clouds. The satellites say the lifting is happening right now at fingernail speed in the present tense. Everything in this chapter is measured. The fossils are in collection drawers. The height is a treaty between 2 governments. The speed is read off orbiting satellites year after year. That is the standard this film holds itself to. And when we finally leave measurement behind, near the end, you will hear me say so out loud. Which leaves the obvious question. If a collision this size is running today in front of the instruments, then this cannot be the first time. Has the planet done this before? It has. And you can walk on the wreckage in 3 different continents. Why do the mountains of Tennessee, the highlands of Scotland, and the Anti-Atlas of Morocco share the same rocks? Lay their geological maps side by side and the folds line up. The same style of buckling, the same ages, the same sequence of layers, picked up on one side of an ocean and set down on the other. These soft, green, worn-down ranges on 3 separate continents are pieces of one mountain chain. Geologists call it the Central Pangaean Mountains. It was raised where continents slammed together to weld the supercontinent of Pangaea. Later, when the Atlantic tore open, the young ocean did not politely go around the range. It cut straight through it and carried the pieces apart. Today, you can stand on the same chain in Appalachia, in Scotland, and in Morocco, with an ocean between each stance. And it was not always soft and green. In 1989, Rudy Slingerland and Kevin Furlong reconstructed what those mountains looked like in the Permian, working from the rock the range shed as it eroded. Their answer was a range of Himalayan type, carrying a high interior plateau like the Andes hold today, standing on average some 4 kilometers tall. Drive the Blue Ridge Parkway now, and you can cross that same range without changing gear. That is what 250 million years of rain does to a Himalaya. The summits are gone, ground off, and washed into the sea. What you are driving on are the roots. The collision that raised them finished assembling Pangaea about 310 million years ago. The supercontinent held for well over 100 million years. Then, about 180 million years ago, it began to tear, and the Atlantic Ocean is the wound left by the tearing. Every beach from Brazil to Ireland sits on the edge of that scar. But the strangest part of the story lies underneath Britain. Before the Atlantic existed, there was an earlier ocean in almost the same place. Geologists named it Iapetus, for the father of Atlas. It was one of the oceans that died to build the Great Chain, and its seam still runs through the British Isles, close to the border between Scotland and England. The proof is in the fossils. The trilobites found in Scottish rocks belong to the American side of that vanished ocean. The trilobites of England and Wales belong to the far shore. Two seafloor faunas that lived an ocean apart now sit a day's walk from each other because the water between them was destroyed. A national border, more or less tracing the ghost of a dead ocean. In 1966, the Canadian geophysicist John Tuzo Wilson looked at that evidence and asked a question in the journal Nature. Did the Atlantic close and then reopen? His answer was yes. An ocean had opened here, died here, and then a new ocean had torn open almost along the old scar. Oceans are born, they grow old, they are destroyed, and their graves become the birthplaces of new oceans. The cycle now carries his name. Which means the word again, in the title of this film, is not a prophecy. It is the planet's oldest recorded habit. Most people watching this are not subscribed. If a seafloor on top of the world is your kind of question, that is easily fixed. Now back to the engine. Because a habit is not an explanation. Something has to kill an ocean. Something strong enough to drag continents across the face of a planet. And for most of a century, even the people who believed the continents moved could not name the force that moved them. What force is strong enough to drag a continent? Most of us carry a picture from school. Hot rock rises at the mid-ocean ridge, shoulders the plates apart, and the continents ride away from the ridge like boxes on a conveyor belt. The push comes from the middle. That picture is mostly wrong, and the correction is the key to everything that follows in this film. In 1975, Donald Forsyth and Seiya Uyeda did the accounting. They sat down with every force known to act on a tectonic plate and weighed them against each other. The push of the ridges, the drag of the mantle, the pull at the trenches. The push from the ridges turned out to be real, but minor. The dominant force in their ledger was the pull of the plate's own dead weight. Here is how it works. New seafloor is born hot at the ridge. The mid-Atlantic ridge makes about 2.5 centimeters of it a year, widening the Atlantic by roughly 25 kilometers every million years. About half the pace India is moving right now. Then the young floor rides away from the ridge, and as it travels, it cools. As it cools, it contracts and grows denser, heavier, meter for meter, than the floor behind it. Give it 100 million years, and the old floor is colder and denser than the hot mantle rock underneath it. It no longer wants to float, it wants to sink, where it finally farbs over and pours back into the earth. At a deep ocean trench, the sinking slab hangs off the edge of the plate like an anchor dropped from a ship. And the anchor does not just fall. It pulls the whole plate behind it, thousands of kilometers of ocean floor, dragged trenchward by the weight of its own oldest edge. Plates are not pushed apart. They are pulled into graves. And this is not theory alone. Seismologists can image the slabs today, mid-fall. Cold tongues of old sea floor hang hundreds of kilometers down into the mantle beneath Japan, beneath the Andes, beneath the Marianas, visible to earthquake waves the way bones are visible to X-rays. Once you see that, you see the death sentence written into every ocean. An ocean's floor gets old. Old floor gets heavy. Heavy floor sinks, and its sinking drags the ocean's shores toward each other. Every ocean is consumed, in the end, by the weight of its own bed. The census of the world's seafloor proves the sentence is carried out. The oldest floor still lying under any ocean out in the Western Pacific is only about 180 to 200 million years old. Nothing older survives anywhere in the deep sea. It has all been swallowed. Meanwhile, the continents carry rock like the Acosta gneiss of northern Canada, more than 4 billion years old. 20 times the age of the oldest wave-covered floor on Earth. Continents are the planet's permanent cargo. They are too light to sink, so they ride the conveyor forever, bumping into each other and breaking apart. Ocean floor is packaging. It gets recycled. Which brings us to the giant. The Pacific is the last surviving piece of Panthalassa, the world ocean that wrapped around Pangaea. It is about 10,000 kilometers across, a quarter of the way around the planet. Board a jet on the coast of Peru, and you can fly for half a day toward Australia and still be looking down at its water. And it is ringed by trenches. The famous Ring of Fire around the Pacific is really a ring of sinking, the longest system of plate graves on Earth, eating the old floor along almost every edge. The Pacific is shrinking by a few centimeters every year. Sail across it, and you are sailing a closing sea. So the engine is identified, and the engine does not idle. Researchers who study the long pattern, among them Hannah Davies, Matthias Green, and João Duarte, put the full cycle of scattering and gathering at somewhere between 400 and 600 million years and place us roughly halfway through the scattered phase. The continents are about as far apart as they ever get. From here, the engine gathers them. Then the next collision is not a distant abstraction. Somewhere on the map, right now, it should already be visible. An ocean already condemned, already closing, already rehearsing its own death. There is one, and you have probably swum in it. Which ocean dies first? And why is it the one with the beach resorts? The Mediterranean does not look like a battlefield. It looks like lunch on a terrace. But it is the last large remnant of Tethys, the great ocean that once separated Africa and India from the rest of Eurasia. And Tethys has been dying by pieces for 100 million years, squeezed out of existence as its shores converge. The collision that lifted the summit band of Everest was one act in that long closing. The squeeze on the Mediterranean is another act of the same system. The rock at the top of the world is far older than Tethys itself. It is the mechanism that repeats, not the rock. And that is worth one slow thought. The floor of this sea, the mud, and the shells settling onto it right now under the ferries and the yachts is a summit band in the making. Somewhere down there, today's cockle shells are beginning the same journey the trilobites finished. The squeeze is on the instruments. Africa is closing on Europe at about 4.5 millimeters a year at the western end of the sea, and up to about 10 millimeters a year at the eastern end. Roughly the pace a child grows in a slow year, and it never stops to rest, never reverses, never sleeps. The Alps are what that pressure has already built. They are the crumple zone of Africa against Europe, folded up out of the closing sea's own floor and margins. And leveling surveys and satellites find parts of the chain still rising, up to 1 or 2 millimeters a year. The collision is not history. The Matterhorn is a work in progress. And this sea has already died once, in rehearsal. About 6 million years ago, the gateway at Gibraltar sealed shut, Africa's slow advance, helping close the door. The Atlantic could no longer feed the basin, and the Mediterranean has a secret weakness. It loses more water to the sky than all its rivers can return. Cut it off, and it does not stay a sea. It becomes a puddle evaporating on a stove. From 5.97 to 5.33 million years ago, the sea largely dried away. Geologists call it the Messinian salinity crisis. The proof came up in drill cores in 1970. Under the floor of the modern sea lies the salt the dying water left behind, a layer more than a kilometer thick in the western basins, up to 3 kilometers thick in the east, around 1 million cubic kilometers of it. Cast as a single block, that is a cube of salt 100 kilometers on a side, standing higher than airliners fly. How empty the basin truly got is still argued about. Some researchers see a desert floor kilometers below world sea level, cut by canyons. Others see vast, hot, poisonous brine lakes that never quite vanished. The emptiness is a reconstruction, and the argument is real. The salt is not an argument. The salt is in the cores. Then the ocean came back, and it came back in a single geological heartbeat. 5.33 million years ago, the barrier at Gibraltar failed. In 2009, Daniel Garcia Castellanos and his colleagues modeled the breach. In their model, the first trickle over the sill cuts a channel, the channel deepens the flow, and the flow deepens the channel, until the Atlantic is pouring downhill into an empty basin at up to 1,000 times the discharge of the Amazon. Most of the refill happens in less than 2 years. Sea level in places rises 10 meters a day. A drowned world made in months. That event has a name, the Zanclean Flood, and it may be the largest flood in the history of the planet. It is why there are beach resorts today. The Mediterranean is a refilled grave. Next time, there will be no refill. In 2024, João Duarte and his colleagues published a three-dimensional model of the arc of crust at Gibraltar. What they found is a subduction zone, a sinking machine, that crawled out of the dying Mediterranean and is now stalled under the strait. Dormant, not dead. In their model, it reawakens and spreads into the Atlantic itself within about 20 million years. Read that slowly, because it is the hinge of this whole story. The death of one small sea can infect a healthy ocean next door. Duarte's team argues this is likely how new sinking zones are commonly born on this planet. The rehearsal does not just repeat, it spreads. One small sea proves the process. But the Mediterranean closing makes a new Himalaya, not a new Pangaea. For the main event, every continent has to arrive. So who else is moving? And when does the whole map finish? If every continent is moving, where are they all going? Start with the sprinter. Australia is moving north at about 7 centimeters a year, the fastest continent on Earth today, heading for Southeast Asia with the patience of a glacier and the certainty of one. That sounds like nothing until it breaks something. By 2016, the whole country had drifted so far from where its official maps said it was that the blue dot on every phone was off by about 1.5 meters. Self-driving tractors were plowing beside their assigned rows. So Australia formally moved itself. The national coordinate system was redrawn to catch the country up with its own position. Look at your own phone's map and consider that the ground under the dot is a vehicle. Australia has traveled about a body length north since satellites began watching. And that watching deserves one beat of respect, because it ended a 70-year argument. When Alfred Wegener proposed in 1912 that the continents drift, he was ridiculed partly for one good reason. Nobody could name a force, and nobody could measure a motion. The idea spent half a century in exile for lack of an instrument. Then, in the 1980s, radio telescopes timing signals from quasars at the edge of the visible universe measured the distance between continents actually changing, year on year. Laser stations bounced light off satellites and got the same answer. Then the satellite positioning network made it routine. The plates move at the speeds the rocks had implied, centimeters a year. It is not an inference anymore. It is a live measurement running continuously on the same system you use to find a coffee shop. So the motion is certain. The destination is not. In 2018, Hannah Davies, Matthias Green, and João Duarte gathered the published futures of the world map. There are 4 serious ones, and they disagree. Some close the Atlantic, and some close the Pacific. One marches everything north to gather around the Arctic. The strangest tears a brand new ocean straight through Asia. 4 maps, 4 names, and the next supercontinent lands on different sides of the planet depending on whose model you read. That disagreement is honest, and it is a story of its own for another film. What matters tonight is the one thing every version agrees on. Whichever ocean dies, the story ends the same way. The continents collide. For the rest of this film, we need one stage to stand on, so we will use the oldest and most studied of the 4 Pangaea Ultima, first drawn by the geologist Christopher Scotese in the 1990s. In this future, the Atlantic slows, stalls, and reverses. The infection you already met at Gibraltar spreads down the American coasts. The old floor pours back into the earth, and the ocean that has spent 180 million years opening spends the next stretch of deep time closing. The Americas swing back toward the Old World. Africa locks into Europe, and the continents gather into a single mass around 250 million years from now, roughly as far ahead of us as the assembly of Pangaea lies behind. Hold that number honestly, because this film promised you it would. 250 million is not a birthday. It is where a family of models converges, and the rivals put the reunion anywhere from 200 to 300 million years out. The date is soft, the event is not. Nothing in any published future lets the continents simply stop, and that span of time deserves one feeling before we spend it. The whole human lineage. From the split with the chimpanzees to this sentence fits inside it 50 times over. Up to this line, everything in this film has been measurement and the recovered record. Fossils in drawers, salt in cores, satellites overhead watching the ground creep. To go further, to actually stand on a shore and watch the collision arrive, we have to cross from measurement into reconstruction. So we will cross. Out loud, everything from this point until I say otherwise is a reconstruction, not a forecast. One path out of an enormous number, built out of things we have measured, and pointed at a future that very probably differs in the details. The teams who built each piece will be named as we go. What does an ocean do in its final act? Stand on an Atlantic shore, some 160 million years from now, roughly as far ahead of us, give or take, as the first birds lie behind. The ocean is old here, and visibly narrower on any map a navigator could draw. It has been closing for tens of millions of years. The ridge that built it still runs down the middle, but the trenches along its edges now swallow floor faster than the ridge can make it. The beach itself looks ordinary. Sand, rack line, gulls, or whatever sings in the gull's place. What is not ordinary is the schedule. The tide does not creep up this beach. It arrives like a slow assault. Kilometers of shore are drowned and stripped bare twice a day. A walking pace advance you could stroll ahead of but never stop. The reason is not invented. It was published in 2020 by Hannah Davies, Matthias Green, and João Duarte, the same team whose long cycle you have already met. This time they ran tidal models across the futures of the world map, and both of the tide facts that follow are theirs. An ocean basin is an instrument. Push water across it, and the water sloshes back with a natural rhythm of its own, set by the width of the basin, the way the note of a bell is set by its size. When that rhythm happens to match the pull of the moon, the basin rings, the sloshes reinforce, the tides amplify, and their models show ocean basins passing through that resonant width roughly every 140 to 180 million years of the cycle. Here is the part that concerns you today. Our own Atlantic is near resonance right now. The big tides you may have watched all your life, the ones that empty whole harbors in Brittany and drain the Bay of Fundy to the mud, are the bell already ringing. In the reconstruction you are standing in, the narrowing ocean passes through the perfect width one last time. The models give this dying Atlantic roughly twice the tidal energy of today's oceans. The kind of range that today belongs only to freak funnels like Fundy arrives on ordinary, straight, everyday coasts. Twice a day, the sea walks inland across whole districts of coastal plain. Estuaries become temporary inland seas the size of counties. River mouths run backwards for 50 kilometers. Then it all drains, and the mudflats steam under the sun until the ocean turns around. Whatever lives on these coasts lives by that clock, a supertide thrown up by an ocean on its way out, and for a few million years it is the loudest thing on the planet. Then the bell cracks. The basin keeps narrowing. The width falls out of tune with the moon, and the ringing dies. In the same family of models, the tides collapse towards stillness as the shores close in, until the last of the ocean lies flat, barely breathing against its beaches. The ocean that spent its middle age roaring goes quiet at the end. The last act of an ocean is violence and then calm. And then the water itself runs out. Which leaves the question this whole film has been walking toward. What happens when coastline finally meets coastline? We are still inside the reconstruction. The numbers underneath everything that follows belong to a climate modeling team, and I will name them as they come. What does it look like the day two continents meet? Not like a car crash. Forget the film trailer version. The shockwave, the single terrible morning. A continental collision arrives at the speed the Himalaya is arriving now. Fingernail speed. The final day is 10 million years long. Watch it anyway. The last strip of sea between the closing shores is a Mediterranean in reverse, a warm channel narrowing by handspans each decade. Its floor buckles first, because the floor is already doomed, old and heavy and half-swallowed. Islands rise that no map has time to name. The channel breaks into a chain of bitter seas, the seas into salt lakes, the lakes into white flats, and then there is simply ground. Ground joining two grounds that used to face each other across an ocean, the way Scotland's rocks now sit a day's walk from England's. No one standing there could tell you the day the ocean died. In every direction, it just looks like land being slowly folded. Then the land goes up. Where the shores meet, the crust doubles. exactly as it is doubling under Tibet today. There is nowhere else for it to go. Every past suture on this planet threw up a great range when the water ran out. The chain whose roots you drove over earlier in this film stood 4 kilometers high when it was young. So the reconstruction raises a belt of Himalayan scale along the closed seam. Thousands of kilometers of new mountains standing where open water used to be, snow on summits that were shipping lanes. And riding up inside that belt goes the sea's own floor. Somewhere in the new range, a band of gray marine rock is climbing toward a future summit, carrying its shells with it. You already know how that story ends, because you have seen the ending. It is the top of Everest. But the mountains are not the killer. The killer is the interior. In 2023, Alexander Farnsworth and his colleagues published in the journal Nature Geoscience a climate model of the finished supercontinent built on the Pangaea Ultima map. What they found is 3 separate heat sources arriving on it at once. First, geography. A single landmass has a single vast interior, thousands of kilometers from any sea. Ocean air never reaches it. Rain gives up long before the middle. Today, the deep interior of Asia is the harshest inhabited climate on Earth, and Asia is one continent among several. Weld them all together, and the middle of the map moves further from the sea than anywhere that exists today. Second, the air. The volcanism of assembly, all those trenches and rifts working at once, pushes carbon dioxide in their model to around 620 parts per million. Roughly half again what the air holds today. Third, the sun itself. Stars brighten as they age, slowly and without exception. By the time the continents finish gathering, the sun radiates about 2.5% more energy than it does tonight. That sounds small. It is applied to every square meter of the planet. All day, every day, with no off switch. The result, in the model, is a continental interior running at 40 to 70 degrees Celsius through much of the year. A land where the afternoon is an oven and the night forgets to cool. For anything built like us, the mechanism of death is precise, and it is not the heat alone, it is the wet air. A mammal is a furnace that must constantly vent. Your core runs at 37 degrees, and the venting works by sweat, by evaporation carrying heat away from the skin. But when the air is hot and saturated, sweat stops evaporating. It runs and does nothing. The heat has nowhere to go. The core climbs, and at around 42 or 43 degrees, the machinery of the body itself begins to fail. Proteins lose their shape. The furnace cooks itself. A mammal lives its entire life 5 degrees below the temperature that kills it. Stand at the edge of that interior, in the reconstruction, and the wind coming off the continent feels like an opened oven door. Behind it lie thousands of kilometers that nothing which sweats can cross in summer. Farnsworth's team ran the census. Today, roughly 2/3 of the planet's land can support mammals. On the finished supercontinent, in their model, the figure falls to between 8 and 16%. Of every 6 acres of land on Earth, 5 become lethal to things built like us. What remains clings to the coasts and to the far north and south. Farnsworth put it in one sentence: widespread temperatures of between 40 and 50 degrees Celsius, and even greater daily extremes, compounded by high levels of humidity, would ultimately seal our fate. Whether anything of our kind is present to be sealed, 250 million years from now, is a question this channel has walked before. And it is not tonight's. Tonight's question is simpler and harder. When the collision is finally over, when the engine has built its mountain belt and its furnace, what survives it? So, the question in the title: when do the continents collide again? The honest answer has bounds, not a date. The gathering is already measurable. At Gibraltar, where a sinking zone sleeps under the strait. In the Mediterranean, closing at a child's growing pace. In the northward march of Australia, fast enough to bend the maps. The published futures put the finished reunion somewhere between 200 and 300 million years from now, and the best studied of them says about 250. And what does the collision do to the world? In the models, this, one last resonant supertide, as the dying ocean rings like a bell. A mountain belt of Himalayan scale along the closed seam, a continental interior that runs at furnace temperatures, and a census in which 5 of every 6 acres of land stop supporting mammals. But the strangest finding in this whole story is what happens afterwards. The supercontinent does not last. Pangaea did not. The ones before it did not. Heat builds beneath a single insulating landmass until it tears the mass apart again, and the cycle that runs 400 to 600 million years starts over. New oceans open through the middle of the New World, the way the Atlantic opened through the middle of the Old one. The map is temporary. The reunion is temporary. What lasts is the scar. The new range will spend the next 250 million years being taken apart by rain. And it will end the way the Appalachians ended: soft, green, quiet. A line of worn hills crossing the interior of a continent that has forgotten there was ever a sea there. Hills that some walking thing will one day cross without ever guessing they were the roof of the world. The mountains are the memory. One last look inside the reconstruction, and then we put it down for good. Somewhere on that future Earth, on a high gray ridge in the heart of the range, a climber, or whatever stands where climbers used to, puts a hand flat on a band of pale rock. The rock is limestone. Inside it are small shells, cockles and sea snails, and the drifting plankton of a warm sea pressed into stone. They settled onto a quiet seabed under a sea that had resorts on its shores. In the years when a species of curious mammals was measuring its planet with satellites and wondering, in the evenings, how much time the map had left. The floor of the Mediterranean. Standing at the top of the world, none of that is a prediction. Let the film say it plainly one time and lay the speculation down. No one has measured the future. What you have watched tonight is a family of models agreeing on a shape, and the shape could be wrong in 100 details. The date could slip. The map could belong to one of the rivals. The range could rise on the far side of the world. But hold the audit of what is not invented. The satellites really do watch India drive into Asia at fingernail speed. The salt of a dried Mediterranean really does lie under the modern sea, kilometers thick in the cores. The same mountain chain really does stand in Tennessee, in Scotland and in Morocco, cut apart by the ocean that was born inside it, and the top of Everest really is the floor of a vanished sea, with the shells still in it. The measured facts all lean the same way. Oceans die. Continents collide. The planet has done it over and over, and nothing in the measurements says it has stopped. So go back one last time to the summit where we started. Present tense, real rock, real wind, a real gloved hand, pressed flat on the gray band. 450 million years ago, the creatures in that stone drifted down onto the floor of a sea that, if a sea can be said to believe anything, believed it was permanent. Every ocean does. The top of the world is always the floor of a dead ocean. Only the ocean changes. Next time on this channel, the fight we stepped past tonight. 4 rival maps of the next supercontinent, and the question of which ocean actually dies, the Atlantic or the Pacific. If deep time is your kind of country, subscribe and walk the next stretch of it with us.